Finally, I'm proud to introduce today's speaker. Joey Logan is a data scientist in the Translational Research Informatics Group, or TRIG, within the Department of Biomedical and Health Informatics. Embedded in urology and pathology, his work focuses on imaging pipelines, data de-identification, and predictive models for radiology imaging and other novel data sets. Joey has also contributed to research on natural language processing using models like BERT and Llama. In addition to developing imaging models for segmentation and classification, Joey specializes in software development and data integration, enabling these large-scale models to operate seamlessly within ARCIS. Again, we ask you to please mute your microphones. Today, Joey will be presenting on machine learning operations for radiology imaging in ARCIS. And now, Joey.
Awesome, thanks, Alex. I'm going to share my screen. Can everybody see my screen?
Yep, looks good.
Thank you. So today I'm going to talk about a specific project and MLOps more broadly. When we think about something like MLOps, this isn't something that necessarily really existed 5 years ago. I think 5 years ago, if you were to talk about MLOps, somebody would be confused and be like, hey, what are you talking about? Basically, what MLOps is it's taking an AI model or even a simple algorithm that's in development or within a laboratory environment. Basically, hey, we're writing a paper, we got some good results, it looks promising, it passed the validation set, and now we actually want to start using this model. Whether we want to use it for research purposes or whether we want to use it potentially even in the future into clinical use. And this is where it gets really, really difficult, I think, because as we all know, if we, for all of us that writes code at any point, is that code and models do a really good job of working on your machine. But when we're talking about broader, super complex models, being able to distribute that to not only run on thousands and thousands of samples, but even in this project, we're actually looking forward to bring this across to multiple institutions. So what I'm going to talk about today is I'm going to talk about the model and the process of it, kind of like more broadly what the actual project was. And then I'm going to talk about what we did to really bring this to life to multiple institutions. So we had a separate study where we had an AI model that analyzed CT images. What it did is it took the CT images, it processed the DICOMs, which are these specialized data formats, which are the pixel arrays plus the tags itself. Grabbed the kidneys, actually segmented the kidneys, because when you're dealing with kidneys, there's two of them, so you have to tell the difference between left and right, obviously. And then wanted to go and see whether or not there was a kidney stone. And if there were kidney stone or kidney stones, because often there are multiple kidney stones, it wanted to determine whether it was the same stone in the baseline image as it was in the follow-up image. And this is super important for the studies because what we want to see is, hey, a lot of these kids, we want to try to avoid surgery. So we want to see, okay, was the stone that they had in a previous exam still there in the follow-up exam? And like I mentioned, we also needed to take our model, which only been really applied for a paper, and apply it to like over 2,000 images. So the first step of the model, just generally speaking, was segmentation. Automatic segmentation was applied to the CT images to identify laterality and to ensure that nothing outside of the kidney was identified as a stone. And this is super important because when you're talking about the bladder and different organs, there could be different kind of artifacts within the body and different organs that would be falsely attributed to a stone, something like a stent or a rod, or even particulates in the bladder itself. The automated segmentation process on the 2,000 or so images took about 1 to 2 days to run in ARCIS, and that's over thousands of studies. The next step is, once we had it segmented, is we needed to measure the stone, and then we needed to do something called registration. And I'm going to take a really deep dive into registration because it's super important. So once the kidneys are segmented, the algorithm can measure the stones and identify if it's the same stone on a follow-up exam. We want to know whether or not the patient passed that stone or not, or whether that was a new stone. We want to see if there was stone loss, whether it was a new stone, or whether it was the same stone a year or two later. This whole measuring and registration process took approximately 4 days to run via Arcus, and that was all run behind the scenes of the Arcus tasks, which I'll talk about in more detail. So talking about registration and why it's so complex, especially when you're dealing with three-dimensional images. So we have two cats that are a year apart. And let's say we want to measure the size of their ears, which in computer vision you can do. Especially when you're dealing with DICOMs, there are measurements within the DICOM tags that enable you to actually to give a good accurate measure of an artifact within the DICOM. So measuring is pretty easy, but we have to figure out, hey, is this left ear here the same as this left ear here? And if, say, there's like a little speck, or let's say, the kitty maybe has like a cyst or something, we want to know, hey, is it the same cyst or is it a different cyst? So one of the things that the artificial intelligence needs to do is it needs to map the follow-up on the baseline. If you look at this image, the follow-up is quite a bit larger. Basically, the pixel array is much larger. And you'd actually have to map this onto the second one. And you notice too, the cats are in slightly different positions. The same thing happens actually with CTs. Even though CTs are a lot more standardized, it can be different, especially when you're factoring in different things like, okay, we have a partnership with Virtua. So here at CHOP, if they have a baseline here, and then they have another scan of Virtua, or, we have the King of Prussia campus. And for our study in particular, we actually had 6 different external sites, and they could have had all different type of manufacturers. So back to the registration, the image that I'm showing you is a 2-dimensional image. Within our study, it's actually a 3-dimensional CT images. So imagine we have different slices. And not only do we have different slices, the slices have different level of thickness. It literally chops up the body as it goes. So the pixel array is different, the number of slices are different, and the slice thickness is different. And why registration is so complex and why you need a process like MLOps to be able to run these very quickly is that you actually need to map this follow-up. You need to fit this follow-up image onto the baseline image, even though it has more slices, even though the slices are thinner, and even though the image itself is much larger. So let's take an example of an actual CT. So in our first image is a very simple near perfect match image. And I know it's tough to tell, especially if you don't look at CTs, but these two are actually very, very different. So the first one's the same. It was a perfect match. It had the same slice thickness. It had the same number of slices, and the patient was in the same exact position. So what that means is you take a look at these crosshairs, that gives you the location of the stone. Because not only do we need to, when we're registering the stones, not only do we need to get the size of it, we need to actually get the location, because we want to see if it's the same stone as it is in the follow-up, as it is in the baseline. If you look at image 2, it's hard to tell, but if you actually take a really close look, you will notice that these two images are very, very different. Even though the stone is most prevalent in this frame right here, they're quite different. There's different organs that are present. The liver's at a different, kind of like in a different area. Even the kidney shapes are slightly different. In this case, there was different slice thickness, different number of slices, and the patient was in a different position. However, the registration process takes this image and it mutates it, and it actually maps it a kidney at a time onto this baseline image. So how did we do that? And how did we do all that in ARCUS? And how did we were able to do that so quickly with all these thousands of images from 6 different sites that have vast amounts of different type of equipment? Basically, I had to apply basically the principle of machine learning operations. So basically, MLOps, what it is a set of tool practices and processes that aim to streamline the deployment of ML models into a production environment. Because even though this is still it still was a research study, we weren't doing for clinical use yet, though we plan to. We needed to really streamline it and bring it into to like a massive amount. So one of the tenets is continuous integration and deployment. So what that means is if there is an update to the model, and we actually had this happen, we ran through it initially, we were able to get results, and we actually found through review, after all that processing for all those days, we actually had a slight bug within the segmentation process. So what I was able to do is basically swap out the model. When I did that, I had to be very careful because I was also writing results to a database. So in my case, I just created a new database where I had like the old results and the new results. You could truncate the database, or you could do different types of locks. So like imagine you're working with some sort of database and you swap out the models. You might want to put as a column in your database, okay, what version of the model are you using at that particular point in time? We are fortunate we only had to do that once. But if you're thinking about MLOps, and my background is actually in finance, where if you're say to do you wanted to do a financial progression where every month you get more data. So because every month you get more data, maybe you're fine-tuning the model. So continuous integration is super important. Reproducibility, obviously the results must be consistently replicated. That means I have to be able to hand my model and the data to another researcher at another institution, and they need to get the same exact results. Talking about different versions, monitoring is super important, and logging. Also in our case, and I think more broadly, when you're talking about kind of the work that we do, is when we're talking about monitoring, we're kind of talking about what is ground truth. And often in ground truth, especially when we're working with the Department of Surgery, our ground truth is the surgeons. So it's literally what their opinion is on your model's performance. Collaboration, in our case, outside institutions needed to actually view the actual images, and they needed a way to transmit these thousands and thousands of images that have a vastly different structure and that are many terabytes to us. And of course, data management and scalability. And we talk about scalability. Our model, it basically needs a GPU, and I'll talk about GPU in a second, and the output needed to be saved to a database. And then the last part, which I kind of added, is just, and I think one of the reasons why, even though I didn't use really any of the fancier MLOps tools, I think I put my major focus on just like the user experience and the ease of use for the surgeons. Very quickly, we're talking about MLOps, we're talking about GPUs. So probably one of the biggest challenge when you're working with MLOps, especially with imaging, is aligning your CUDA with your PyTorch. And basically what a GPU is, a graphics processing unit. Here's like a version of kind of like an older, and it's an electric circuit that processes graphical data and performs mathematical calculation at high speeds. These are very desired. A lot of different places need a lot of GPU. ARCUS has actually really great GPU through their ARCUS tasks. CUDA is a parallel computing platform that basically allows developers to use GPUs for general purpose processing. When you're dealing with this, and this is just generally good advice anyway for any data science project. However, when you're dealing with MLOps, virtual environments are non-negotiable. You need to have them, often because the dependencies are very fragile, especially with PyTorch. Imaging models often require GPU to run. And what I had to do to really align those, I actually had to develop special helper scripts to make sure that everything was aligned as far as the GPU, the CUDA, and the PyTorch version. Our next challenge is the data transfer. So we had these 6 different institutions with hundreds of images. We needed a way to get them. And these images are so big and the structure is so complex, you just can't drop them into a Dropbox. It just literally won't work. It'll just get too big, and the structural could potentially get messed up too. So we have an instance of Ombra. And the instance of Ombra that Arcus and Trig uses is different than the Ombra that you hear about through CHOP. We have our own instances, which is really nice. And what Ombra allows us to do is sites are actually able to upload those images right to us. So here's an example of our butterball turkey X-ray. And here they were able to actually put those in mass, and the sites themselves, they were able to view and edit the images and edit some of the like the study ID and things like that, because study ID was really important for them to label what images were what. One of the big parts, unfortunately, I didn't have a big part of this, but is the data use agreements. We're super complex. Fortunately, we have a great team that was able to handle that without me. Typically, when you want something from an outside institution in Arcus, they have to be onboarded as a CHOP NTP, which is actually somewhat of a simple process, or at least Antoine from Dr. Tajin's team makes it look simple. And they have to do a background check, and they have to do their city training. But when they do that, they're actually given access to a virtual machine to use the CHOP VPN and log into Arcus. I talked a little bit about the analysis step before. It starts with getting the images from the sites. The sites went into Ombra. The images went into Ombra. From there, we were able to do the tag mapping. We were able to transfer the image to a 3-dimensional, the slices of image into a 3-dimensional images, segment the kidneys, and then do the actual processing itself. So from there, okay, we have all these images. They gave us these images. We processed them. We have results. We want to know, hey, are our results right? Like, is everything looking good? Do they have some sort of agreement before we actually report these results out? So we had a pathway to bring outside researchers into the lab, which is great. Arcus has all the tools needed and an outstanding programming and development environment. However, what we need to do is actually look at these 3-dimensional images. Arcus did not have a viewer that was able to display 3D nifty images. So we actually found a web-based viewer called Papaya, and all Papaya is 8,000 lines of JavaScript. That's literally what it is. And that 8,000 lines of JavaScript is a viewer. So Arcus was nice enough to spin up a web server for me, and they put this nice little widget right in within the lab tools. So when an outside researcher was able to go and look at the images, I gave them the results, and they wanted to see, okay, were the results of the algorithm right? Is this stone actually 3 millimeters long? Is this stone in the same as it is in the follow-up? So they were able to spin up this image viewer right here for me. And then it was kind of up to me to create a website. And the reason I needed to create a website within that image viewer widget is I need to serve up the images for them. Like I said, the image viewer itself is 8,000 lines of JavaScript, and you had to kind of like let it know what image it needed to go looking for. We had thousands and thousands of images, so I had to create like this little kind of like very basic JavaScript search bar where they were able to put in the actual study ID and they could see the pre and the post or the baseline and the follow-up. So from there, when they were able to go in and actually serve up the images, they were able to actually view the images. And not only were they able to view the images, you could actually zoom in, you could switch views, and you can actually measure the stone itself. I needed to create really detailed documentation, and I actually even recorded a demo video for the reviewers to use the tool. And I also assisted the reviewers when needed. I have kind of like a background. I play a lot of blitz chess, so I'm able to click through things very, very quickly, which is actually really handy for this. So I'm able to zoom and find a stone in like 2 seconds. So it's a big help for them if they're having difficulty. So let's talk about results. So we had 3 viewers, and they were all given a sample of the results. Each result had two reviewers, with a third breaking a tie if needed. And basically what the reviewers needed to do is they needed to say, okay, hey, do I agree with the algorithm or not? And the results were very positive. I think we were only really found that the algorithm was only incorrect once, and I'm putting that in quotes. And the reason why is basically it was misclassified as a calcification, I think, in the kidney's renal vein rather than the stone within the kidney itself. Basically, the algorithm kind of segmented this portion of the renal vein as part of the kidney. But that's totally actually normal behavior, and the image quality of this particular image was also very, very poor quality. So even though this was kind of like marked against us, I actually think it actually performed well, at least finding that classification. We actually had a representative from the NIDDK that took part of in reviewing the discordance, which was very helpful because not only did they kind of keep us in line, I happened to notice that the reviewers themselves, they were like so particular, but the NIDDK kind of like really reassured them, and they were very pleased with our results. So talking about the impact of this study, so each kidney for each CT had a range of stones from 0 stones to potentially dozens of stones. It would have been impossible for reviewers to identify and catalog them in the CTs. It would just you couldn't have done it. It would have taken years. And we even found that even when we were reviewing, even the reviewers kind of had a little bit discordance with each other. What's great about these automated algorithms, though not necessarily perfect, is that they're very consistent throughout. Partially due to this work, we were actually awarded a multi-million-dollar grant over 5 years with a possible 5-year extension. And our next step, so we went from about like 2,000 to 2,500 images, is we're actually, there's going to be actually several outside sites that are going to use this model to catalog stones over about 250,000 images. So basically best practices for deploying a model into production. So it's like, okay, hey, I have this model and I want to start using it. So what my recommendations from my experience would be is you can use a fancy MLOps tool if you want. I think your focus should first be on user experience. You need to make it very, very simple, especially when you're dealing with PIs, for them to be able to use your tool and get results. That's actually the most important thing. You have to do great training and documentation for stakeholders. And in the case for this, I think for maybe like a month or two, my job was very similar to help desk, because I had to help them get into Arcus. I had to help them get on to the VPN and everything like that. Also, consistent feedback from users. So as we're progressing, we're even fine-tuning this same model for the next step to this day, is that you need to have consistent feedback from the users, and kind of building those relationships are so important, because finding ground truth is so difficult like I mentioned in finance, you know what the truth is next month. You know what your revenue is going to be. In this case, if you're having a result, like let's say a measurement of a stone, and your AI does that measurement of stone, that means an expert actually has to go and verify that. So consistent feedback is huge because that is your training and retraining data. I think, especially in our case, rather than, I think a lot of times, sometimes people rely heavily on a vendor or or consultant or something. I actually feel that like self-developed code and systems are an asset, not a liability, because we had so much flexibility to build whatever we want. This seems like a simple one, but this is like a bad habit that I've been breaking. It's that when you're getting results, especially model results, is try to have them feed into a database and not just like a CSV, or else you're just going to be juggling like 50 different CSVs, and you're going to be naming your CSV underscore final underscore final final. You know, we've all done that at some point. So try not to do that. Obviously use a virtual environment and catalog your changes. So if you have to upgrade your PyTorch, just catalog that in your database somehow. You want to test any changes first in development. If you can, I actually had a development portion within Arcus before pushing it to production, which is super helpful because I'm not a web developer by trade. So before I needed to push it, I needed to make sure I didn't actually break anything. And then use Argus tasks, which are phenomenal. They're faster, number one. And number two, they run behind the scenes and they actually give you an email when the process is complete, which is great. Especially if you're doing it in several steps. And obviously break it into several steps and that way you can reconcile each step separately. And obviously lots of logging. So whatever your model's running, whatever your code's running, try to do as much logging as possible, because if something does break, and things invariably will, you will be able to at least see where it kind of got busted. So just talking a little bit about our tech stack and then some of the other MLOps tools that I sort of looked at. So our stack is our code, really. So our stack is Python with many of the popular imaging libraries and a bunch of bash scripts. Argus Task, which is phenomenal. I highly recommend it. For a viewer, we use Papaya. I am kind of looking for a better viewer. I did get some feedback on that. The viewer's fine. The measuring tape on it is not the best. It kind of gets in the way a little bit. Locutus, and what Locutus is Locutus is actually our homegrown way of de-identifying and delivering images. Ombra, which is, of course, the way that outside sites can contribute studies to us. Everything is GCP in Argus, everything's in the Google Cloud platform. And if you ever need to like build a website really, really quickly and efficiently, it doesn't necessarily like look the best, but I use this Python library called Jinja 2, where I was able to kind of spin up that website for them to serve up the images, and it was super helpful. It was also very easy. It's just like a couple lines of code, and it produces so much HTML for you. It's really nice. GitHub, of course, you want to document any changes, and Google BigQuery. So when you're in Arcus, not a lot of people know this. Not only can you query the ADR from Arcus, obviously, depending upon your identification levels, you can get some data about your cohort. You could actually create your own database and your own tables right within Arcus, which I highly recommend doing. Some of the other popular stacks, one is Flywheel. I think Flywheel is the most popular MLOps tool for imaging. I'll talk about that on the next slide. And some of the other basic ones, weights and biases and MLflow. I think those are more suitable if I had a lot of changes to the model. I didn't. I only had to change it once, which was nice. I think if I had to do continuous upgrades and continuous retraining and redeployment on a weekly or daily basis or monthly basis, I would probably want to use, the stack. And then if you ever work with LLMs, LangChain is pretty much the default or one of the default kind of like MLOps tools, or at least that I've used. And then from there too is we did bring this model into Flywheel, although we didn't wind up using it there in Flywheel. Yeah, it's a popular MLOps tool for imaging. We deployed this process using via custom Flywheel gears. I guess my strike against Flywheel is it didn't have really good interaction, like a database connection on the cloud. You have to basically do all your processing locally, push it into the cloud, and then you get all your data back to your local environment to save it to one of your databases. And I feel like it was kind of like clunky and awkward. Also, you're at the mercy of a vendor where you basically would have to beg Flywheel if you needed something special. I did not like their viewer. Actually, I thought their viewer was poor, especially for 3D images. Like I said, you had to rely on vendors rather than, hey, within Arcus, we can actually create custom solutions. And that's all I have. So happy to field any questions.
Yeah, we ask for questions that you either write in the chat or raise the hand up by the next to the people. The first question is from Gerard.
Hi, thanks, Joey, for your talk. That was fantastic. My name is Gerard. I'm recently joining DBHi from a PI in hematology, studying sickle cell and using AI for predicting early death. And so this was very, very interesting. And I had a couple questions. One, regarding the question around the deployment. I wanted to know if there was any thought or talk about deploying back into the EHR environment, like for example, doing this in Epic and getting it into the sandbox somehow, like as an application, and wanted to know like what your thoughts were about doing this, and would there potentially be some issues with processing and since these like images require like a lot of CPU power. But yeah, I wanted to hear that. And then I'll raise my hand again.
Yeah, no, that's
another question.
That's actually a great question, because that is something we are working on. So talking about the actual processing portion, if we were to do that, that would likely occur in Flywheel, where we would pull the image from Epic, or really from the PACS system, run it through Flywheel, get the output, and then feed it back in to the EHR. It's so tricky though for a number of reasons. Image delivery takes place through radiology, and we're actually very fortunate. We have a great radiology systems team that delivers these images to us. But we actually have to put in a formal request where they drop these images into our own PACS system. There's no way that exists today, like an API call, where you cannot currently reach into the radiology PACS and pull out an image and then do something with it. They are working on that, and I believe actually next year they're hoping to make a research PACS to do that. And the reason why they need to do it in a research PACS is because our PACS system is live. So that means radiologists and surgeons actually need that PACS system totally stable for clinical use. For like, a patient can't, we can't crash the server while a patient's on an operating table, right?
Sure.
With like giant massive API calls. So I believe what they're hoping to do is kind of mirror, like create a research PACS system that mirrors the production PACS, and then hopefully have an API, pull that out, push it in the Flywheel, process it, and then back to the EHR. So that's the plan. I'm not sure where radiology systems is with kind of creating that. That's a very big build, but I
Sure.
know that's on the radar.
Sure, that's awesome. And thinking through that line of thought, perhaps not even the images need to go back to the radiologist, but the results of
The results.
the model, yeah.
Yeah.
And then the second question that I was going to ask is regarding like sickle cell nephropathy, which is a little bit more like diffuse of findings that would be found on a CT scan versus
Mhm.
in this case, you have kind of something that's finite, able to be seen in
Mhm.
because it's a stone and it has like, you know, well demarcated borders. And I just wanted to know like, I guess your thoughts around an approach where you see some more like diffuse changes, and would you have used the similar like modeling approach, or um would it be different if they're like, for example, like we know like it's in like what specific area of the kidney, like in the cortical area, you would see these changes.
Mhm.
Um, but I want to know like, is there a different approach when it's not as well demarcated as a stone, for example?
Yes, yeah, and I think there's a couple different ways of approaching a problem like this. A lot of research we do is on hydronephrosis of a kidney too, which sort of is actually like the dilation and fluid within a kidney. And we've done studies in the past where we've like labeled the hydronephrosis level or indicated whether or not yes or no, sort of like more of like a classification algorithm rather than an actual like measuring algorithm. So those are a little bit different where if we were it, and I'm thinking theoretically, if we wanted to push, let's say, the hydronephrosis model into production, likely we would give some sort of probability back, right? Because
Mhm.
it's a harder problem, right? And you're right. It's like stones are actually, I don't want to say easy, but they're pretty easy. The hardest part of doing of labeling a stone is worrying about mislabeling if it's like a stent or something like that. But
Right.
if it's a bright stone, the algorithm's not going to miss it, which is great. But some of the harder ones, it might be a little bit difficult. And I think too, and I think with AI and more broadly speaking, especially as we're talking about using AI and putting that back into the clinical part. I know a lot of that. There's an office of like artificial intelligence within CHOP, and I think really working with them because we do have to be very careful, right? Because we are getting results, and where the results, may or may not be 100%, right? Because
Right.
if a clinician's not 100%, then certainly the AI is not going to be 100%. So you'd have to be very, very careful about that, especially, kind of, I think the biggest hurdle with that isn't technology. I think the biggest hurdle is policy.
Sure. Sure.
Thank you.
Thank you so much.
I think the next question comes from John from the chat. There are a lot of open source solutions for the different steps you outlined. When Argus does a project like this, how are they sure they don't reinvent any wheels with respect to analysis pipelines?
Gosh, I guess that's a really good question. Because it could have been, well, one, there's a lot of good documentation about stuff like Arcus tasks. Uh, in this case, it could have very well possible, and I think that's one of the I guess downsides of research groups being so siloed actually is that I do feel at times that we can be reinventing the wheel. Also, I was very kind of like fortunate when I kind of started out this process is that I kind of looked at some of D3B's processes and what they were doing in Flywheel, just generally speaking, because I wanted to explore Flywheel as a solution. But I did find kind of like when I did a deep dive in it, and it was actually very nice that they kind of allowed me to create a sandbox on their flywheel, and I found that really flywheel wasn't right for this project.
Thank you. I think Tom Reynolds, you have your hand up.
Sure. Joey, that was an awesome talk. I've been hearing you talk about this process for a couple months now, and it's really nice to actually see it end to end. It's really tremendous. Thanks for sharing today. I have a question that follows on Gerard and John's, and that has no creativity or uniqueness to it. But just to follow on, I think it's such an important topic. Like, what would you recommend if I wanted to start measuring something tomorrow? Like, where do I start? Like, how do I not reinvent the wheel? How do I pick up where you left off without stealing your homework? And what would you recommend to other people who are inspired by your talk and your progress today?
I mean, I think the first step with that is honestly, I think it kind of starts with Arcus, and the reason why, and particularly within an Arcus lab, is that it had all the tools I needed to do. It had everything I needed, and what it didn't have, they let me build. Right? It didn't have a way to serve up the images. It didn't have a web server, and they allowed me to spin up a web server. So I would honestly, if I want to do kind of research, is I would actually start with Arcus.
Yeah, great. Thanks, Joey.
That's all the questions we have. Thank you, Joey.
Well, great. Thank you, everybody.
Looks like Asif has one question that just popped up in chat, and I can go ahead and read it aloud if you'd like, Alex.
Sure, read them.
Okay, here you go, Joey. Fantastic work, Joey, and nice presentation. Any thoughts from this work on framework for model choice and model management? How is the team thinking about tracking, managing models, drift and ensemble models? Again, great work. And thanks for the question, Asif.
Yeah, and that's a great question. And I think that's where, now that we're sort of getting a little bit more advanced, I think this is where we start to get into some of those more like popular ML ops tools like ML flow or weights and biases, and see if they basically have kind of like what we need for rapid deployment, rapid results. Fortunately for this project, like I mentioned, we only had to reconfigure the model once. For the next step, we have a lot of changes to it, but it's not like it's such a living thing where it has to be reconfigured every often. For ensemble models, that's also a very good question that we have to think about. And I think tools like ML flow and weights and biases, I think they do a lot of the heavy lifting for you. And if we don't feel like purchasing those because I believe they're a subscription, I almost feel like I would just do logging within the database and just kind of keep it simple, because that's what I did with this project. Is that I didn't want to rely on vendors, so I had to just log the version of the model. I had to log right within Arcus, right within that Google BigQuery. Is pretty much what I used to track all my changes from start to finish, which is super helpful.
All right, I think that actually is all the questions. Thank you all so much. And thank you, Joey, for presenting on this incredible topic. We appreciate it. Have a great day, everyone. Thank you.
Happy
Thanks.
holidays.
Happy holidays.